I'd like to welcome our speaker today. Raj Rajamani has been here at the university since September 1998. So if I do my calculations correctly, this is your 20th year. Yeah. Okay, wonderful. Professor Rajamani received his PhD back in 1993 and worked for several organizations before coming to Minnesota. He published a textbook, Vehicle Dynamics and Control, in 2 editions now. The last version is in 2012. He's worked in vehicle dynamics, intelligent transportation systems, sensors, and control system design applied to many different applications. Has published, co-authored several hundred journal papers and received a number of awards, including the NSF Career Award, several Outstanding Papers Awards, and we're very honored to have him speak on this latest project related to bicycles, smart human-centered collision prevention systems for bicycles. Raj?
Thank you, Max, for the introduction and for inviting me to talk about our project. So this is about a collision prevention system for bicycles. So I'll start by acknowledging, that this work was entirely done by others, and although I'm doing the presentation here, and as we go through the slides and the different parts of the project, I'll talk about who did which part of the work. So we were initially funded by the Roadway Safety Institute for a couple of years, and so we did our initial part of the work with that funding, and then subsequently we got some NSF funding, and so our work is under the NSF umbrella now. Okay, so from a high level perspective, what is the grand objective of our project? What we're trying to do is develop a smart collision prevention system for a bicycle. So basically our objective is to install sensors, develop estimation systems for a bicycle so that we can track all the nearby cars from the bicycle. And then we can predict the trajectories of the nearby cars. If there's a danger of a collision, we can provide a warning to the car. And essentially that warning is going to consist of an audio-visual signal. So it's based, you can think of it as a honk, right? So you can have a visual signal in addition to a honk, and so the objective is to wake up the motorist or alert the motorist to the presence of the bicycle. So what is difficult about doing this? What are the challenges here? So one of the challenges really is that the size, cost, and weight constraints on a bicycle are very significant. So on a bicycle, we want to constrain the total allowable cost of all sensors and electronics to be $500 or less, so that it's appropriate for a bicycle. Yeah. Now, if you compare the cost with a high-end sensor like the LiDAR sensor on a Google self-driving car, that sensor can be as much as $80,000. So you can see what the difference is in terms of cost. So while we have a very significant budget constraint, our tracking challenges are pretty significant. So if you were developing a forward-looking sensor system and you were tracking cars for a forward collision prevention system, that would be a relatively easier task. On a bicycle where you're riding on an urban road, you're going through traffic intersections, and there's a lot of things happening at a traffic intersection. There's cars that are going across, cars that are turning right, cars that are turning left, and so on. So the tracking that you have to do and the estimates that you have to make about what is going on in the traffic intersection, that is a lot more difficult. So we have a very constrained budget and we have a very difficult tracking problem. Okay. So crash statistics, there's typically over 49,000 crashes between cars and bicycles that happen every year, and over 700 bicyclist fatalities. So some interesting features of these crash statistics. 41% of these crashes happen at traffic intersections, and another 40%. So basically, overall, about 80% occur very close to traffic intersections. And then if you look at the maneuvers that happen just before a crash, in the case of a bicyclist, it's bicycle riding in the same direction as a car. So rear collisions really between cars and bicycles. So basically a car hitting a bicycle from the rear, that's about 45%. Bicycle riding across an intersection where it could be a rear or a side collision, that is pretty high. In the case of a car, it's typically a car that's just going straight or is making a left turn. Okay, so with that in the background, what we decided is that we'd work on these types of collisions. So rear collisions, right? So basically the bicycle getting hit from the rear, right turns. So at a traffic intersection, a car turning right that hits the bicycle, and then side collisions while a bicycle is going across a traffic intersection. So especially intersections with a left turning car. Okay, so we'll talk about each of these systems, one at a time. Okay, so rear collision prevention. So this work was done by Wongsun, who worked on the initial project with RSI funding and helped us get the NSF project. So rear collision prevention, basically what we're doing is we need to have a sensor at the back of the bicycle so that you can track cars behind the bicycle, right? And measure distances and predict trajectories of those cars. Now you can't use LiDARs and radars because they're expensive. You can't use sonar sensors because sonar sensors have typical range of maybe 5 meters or so they don't have adequate range. What we can use instead is a single beam laser sensor. So single beam laser sensors, they have adequate range. They have some disadvantages like low sampling frequency, so you're not going to get very, very quick updates from the laser sensors. And then they have narrow laser beams. So because the laser beam is narrow, you're going to have to rotate your laser beam in order to track as the car moves, right? As the car moves laterally or longitudinally, you either have to track the car, control the laser sensor so that it is facing towards the car at all times, or else you have to do some kind of a scanning so that you know exactly what is going on behind you. Okay, so this is the laser sensor that we use. It's inexpensive. It's an $89 sensor. It's got a range of about 35 meters. Pretty good resolution, 1 centimeter, and 50 hertz updates like I told you. So it's mounted on a stepper motor, so we can control the orientation of the sensor in real time. Okay, so what we do is, we initially do scanning of the road behind the bicycle. So that's what we need to do in order to see if there is a car behind the bicycle. And then once you find an object in your 35-meter range, then what you need to do is you need to find out if that object is a car or not, right? And then so we do things like clustering. We reject outliers. We find out if the object is a car. After we do that, then we can find out if the object is a car, but we cannot actually just keep doing open loop scanning. So this video is an animation from simulation. So this basically shows you what happens if you just keep scanning. So in this case, we are just scanning the rear. And if you keep scanning the rear, only occasionally you're measuring the distance to the car. So most of the time, you're not measuring anything to the car, so you cannot actually track the car on a continuous basis. So if the car makes a sudden maneuver, you're not going to be able to catch that in time. Yeah. So you get relatively sparse data, as you can see here. You're not getting continuous updates. So instead, what we do is once we detect that it is a car, we try to track the right corner of the vehicle. Okay, so we use something called receding horizon optimization. So what we're doing essentially is we are predicting where the car is going to be. So we have a model of the car, and using the model of the car and the measurements, we basically predict where the car is going to be. We have a receding horizon over which we're making the calculation, and we optimize where the sensor should be oriented in order to maximize the chances of being able to hit the right corner of the car. And the reason why we want to hit the right corner of the car is because then we get both the lateral and the longitudinal distances to the car. If you hit the front of the car, you really don't know where you are laterally, and if you hit the side, then you don't exactly know where you are longitudinally. And if you hit the right corner, then you know both the lateral and the longitudinal distances. So we need to do two things. We need to have an optimization control system that basically decides what the real-time angle should be at every sample time, so that you are tracking this point. And then in addition, so that depends on the prediction that we are doing, right? Now in addition to that, you also need to track the car. So you need to have an estimator or an observer that basically predicts what the car is going to do, right? So you need to so those are the two parts of the algorithm. There is the receding horizon optimization, and then there is the vehicle motion estimation algorithm. Okay. So here's an example of how the system works. This is again the same kind of simulation. So initially we were doing open loop scanning, but then after the first scan we understood that it was a car, and then we started tracking the right corner of the car, and then we can keep following the car as it moves. So you can see the first scan was able to tell us that it was a car, and then after that we are able to keep tracking the right corner, and as the car turns, we are able to track the car. And you can see that in this case we get continuous updates of data. So here we are able to really find out what is going on in real time. Okay. So we implemented this system on a bicycle, and so this video here is basically taken at the height of the sensor, the laser sensor. So you can see the laser sensor doing the tracking and the car behind it. So this is initial scanning going on, and then now the sensor found the car, and after it found the car, it just keeps tracking the car. Oh. Okay. So I have a couple of videos here on this rear collision system. Okay. So this video basically shows you what happens, how the system responds essentially when this car is traveling very close to the bicycle. So basically it doesn't actually turn towards the bicycle, but it's a bit too close laterally. It's a bit too close to the car, and so a warning is provided to the bicycle, to the car. Okay, so I think the audio was able to play through the HDMI, so it's good. So yeah, you can basically see that the system responds, and here is another video. In this case, the car turns towards the bicycle explicitly, and then it receives a warning. So we have a lot of videos of this kind, many different scenarios of rear cars behind the bicycle. Okay, and then we've done some real world testing with this as well. Basically, just riding this on the road and try and seeing how well it does. So this is one of the newer bicycles, and this is a temporary setup on the bicycle where we have a convenient platform where we can drill holes and install anything we want essentially. And you can see the laser sensor and the stepper motor, and then this is a video camera. So these are all installed on this platform here, and this is where the battery and some other electronics is located. So this video, I think it's on Fifth Avenue or something like that, near the university. This video is going to show you just a real, just the bicycle riding on the road and tracking many different cars. Okay, there's no warnings or anything provided. So we do that only when we do our control tests, right? We're not yet ready to start creating a lot of sound on the road. So you can see it tracks all the cars that come behind the bicycle. So one of the modifications to this that we are implementing is basically where the sensor doesn't completely follow the car even as it goes past the bicycle, but hands off to the side sonar sensor. So right now you can see that in what the sensor is doing is it just keeps following the car even as the car goes completely past the bicycle. So that's being changed so that the sensor follows it to some extent and then hands off to the side sonar sensor so that it can go back to tracking what is behind the bicycle. And if you look at the data in some of these real world riding tests, you can see what the sensor is doing. So this is the sensor orientation. So basically the sensor follows the car, right? And then once the car goes past the bicycle, the sensor goes back to doing open loop scanning. So this is where the sensor is just doing open loop scanning behind the bicycle. Then it finds a new car, it tracks the car, follows the car, then once the car goes past, it goes back to doing open loop scanning and so on. Okay, and basically our estimation algorithm, you can see how the estimation algorithm works. So if you just use the raw data from the sensor, you can see how the raw data is spread quite a bit, and there's quite a bit of noise in it, and there's all kinds of outliers in the data. But using the clustering algorithm and the tracking algorithm, you can get a more smoother estimate of what the car is doing. Okay, and then we've done some work on a custom sonar sensor for right turn tracking. But I'll skip that and I'll go on to the next subsystem. Okay, so this is about collision prevention with left turning vehicles at a traffic intersection. Okay, so the objective here. So what we did so far is we talked about tracking cars behind the bicycle. Yeah, so this is about detecting and tracking opposing direction vehicles at a traffic intersection. Okay, so the bicycle is going in this direction and the cars are going that way, right? So it's opposing traffic, and then this is a vehicle that might be turning left. Okay, so our objective is basically to identify left turning cars or cars waiting to turn left and predict danger of a collision with a left turning car, provide an audio visual warning to the left turning car. Okay, so for this task we use a low density LiDAR sensor from a company called LiDAR Tech. So this is relatively low cost, maybe about $450, or just a little bit less than $500. Okay, so it's somewhat expensive compared to the rear laser sensor, which was much cheaper, right? But what it gives us is it has 8 segments, so it has 8 laser beams, right? and so it can measure distances to 8 targets. Okay, so that's called a low density LiDAR sensor, because the more expensive LiDAR sensors like the Google sensor that I was showing you earlier, that has a tremendous number of points. So that's got a tremendous number of points that it measures simultaneously, while this it only measures 8 points at a time. So it's a low density LiDAR sensor. So this particular sensor that we bought has a 48-degree field of view, and a typical application for this sensor would be a forward sensing and tracking application on a highway. So basically, on a highway, all the cars are going in the same direction. If you have a laser sensor and you've got 8 beams on it, you can track all these cars that are in front of you, right? So what has not been done, as far as we know, is actually using a low density sensor like this one to track the traffic in a traffic intersection, to track the vehicles in a traffic intersection. So in a traffic intersection, like I said, there's left turns, right turns, cross traffic, a lot more complicated things going on. So using a low density LiDAR to track the vehicles in a traffic intersection, that's the research problem that we are actually working on. So for the left turning car detection, the sensor is actually mounted here. So this is just ahead of the pedals. So the rider's legs are not really going to interfere with the sensor, because the sensor is just a little bit ahead of the rider's legs. And this is something that is still under development, but this is where currently the optimal sensor location seems to be. And everything on the system on the bicycle is basically all the control systems are implemented with the Teensy microprocessor. Okay, so first of all, the field of view, is that enough for tracking all left turning cars? So we're going to use this LiDAR sensor without actually doing any rotational control. So it's going to be a fixed LiDAR sensor. So unlike the rear collision where we did active control, right, here we are not going to do any active rotation control. It's not going to be on a motor. It's going to be a fixed LiDAR sensor. So then the question is, given that it's fixed and it's got these 8 beams, can we track all left turning cars independent of what the size of the road is and how many lanes there are? And basically some simple analysis shows that it is indeed adequate to have this field of view, and whether the road has 1 lane or 2 lanes or 3 lanes in each direction, for all those cases, we can always find the left turning car with this sensor. Okay, so essentially what we have is basically a sensor with 8 beams and no rotational control. And because we have no rotational control, it's a stationary sensor. Some of the questions that are going to come up are, you might be only getting one reading, only one of the beams might be on the sensor. So how do you detect that it is a car? How do you, how do you associate each reading with a particular track, with a particular car? Feature extraction is a challenge. So if we were doing scanning, we would be able to essentially scan the L portion of the car and really find out where the right corner is, and then we know the longitudinal position and the lateral position, but we don't have all that information because it's a fixed sensor. We're going to just get one reading off of the car, and we have to find out all the information that we can. So what we do is we have essentially estimation algorithms for tracking what each car is doing, and some of the variables we track are the lateral and longitudinal position, the orientation, the velocity, the orientation variables, and then one more variable which is essentially the distance. So we'd like to track one point on the car, and ideally that point would be the left corner of the car in this case, because that would give you both lateral and longitudinal positions, but we don't really know which point on the car the sensor is going to read. So what we need to do is we need to keep updating the value of this point no matter exactly where you actually measure the car. Okay. So this epsilon y basically gives you the distance between the point at which we are measuring and the point that we are trying to track. Okay. So So what we have is we have equations for the lateral and longitudinal positions, the orientations and the velocities, and we have equation for the distance between the measurement point and the left corner of the car. So essentially, if the car was traveling straight, these values would be they would not really contribute, and epsilon y dot would be equal to v. So basically, as the car is just moving straight, you'd be just moving across the front of the car. So epsilon y dot would be equal to v, but because the car might be turning and might have a velocity that is not right along the car, so there is all these other terms there. So basically, we have equations for all these variables, and we have if the car is very far away, then because the signal to noise ratio is quite bad, we don't try to estimate the orientation in that case. In that case, we just do the distances and velocities, and if we are closer, if the car is closer to the bicycle, then we try to estimate all the variables. Okay, so how does it work? So this is an animation, and the data is right next to it. So basically, you can see both the straight car and the left turning car being tracked. So the squares that you see on the cars, those are our estimates essentially. You can see the raw readings as well. So here you can see that for the car that was going straight, this is what the data looks like. So these are the real positions of the car, basically the positions of the two corners of the car. Yeah, and so our sensor happens to hit the car at the right corner in the beginning, and we don't really know where the left corner is. But after a few samples, we're able to pick out the left corner, and then once we pick out the left corner, because we have all the update equations for epsilon y, then we're able to keep tracking the left corner. So largely, most of the time, we're able to track the left corner pretty nicely. Yeah, and then you can see the same thing over here for the turning car. We happen to hit the car. The first laser beam happens to hit the car at some location, but after a few samples, we are able to find the left corner of the car, and then our equations are they're not going to be very good for a turning car. They're much better for a straight driving car, but we do a reasonable job of tracking what the car is doing. Okay, and just for fun, if we didn't have all these models and we didn't have these estimation algorithms, right? A more naive approach would be to basically say that I'm going to measure whatever the laser sensor measures, right? I'm going to associate that data with the right car. And then if there's more than one beam on the same car, I just take average of the two beams, and and that's going to be my reading. So that would be a simple way. If you didn't have any estimation algorithms or any models or anything, that would be the simple way to track a car. And if you did that, this is what you'd get essentially. So if you didn't really try to track exactly what the car is doing and how epsilon y varies, then basically your estimates of what the car is doing would vary quite a bit, because you are essentially moving across the front of the car. Your laser beam is moving across the front of the car as the car is moving. Okay, so basically all these models and estimation algorithms, they really do play a role, and they give you much better estimates than what you would get if you just used raw readings. Okay, so this is a video of this system, this LiDAR system, low density LiDAR system, being driven on the road. So again, just like in the animations, the squares are going to represent the estimates of the vehicle position. Okay, so the squares are going to represent that, and the raw readings are going to be given by the X symbols. Okay, so let me play this video here. So you can see that the car is being tracked, and then there's a second car coming up there. Okay, so and I mean, I think the difference is that the raw readings, essentially, you get a lot of outliers, you get a lot of raw readings, but the estimates are smooth and continuous, and they're more reliable. So you can see that the squares don't jump around all that much. Okay, so this is a system under development. This is, we need to do a lot more testing with this system. It's a relatively newer development for us in the project, and so we'll be testing a lot more with this and seeing how well it works out. Okay, so then I'll talk about a couple of other systems on the cars. I mean, on the bicycles. Okay, so one of them is a hub Dynamo system, and so this work was done by Peter Kelly, who's an undergraduate student in the department. And so here, what we did is we installed a hub Dynamo on the rear wheel of the bicycle. So it's a Shimano system, and it's basically an electromagnetic energy harvester. So basically harvests energy, and so normally it would be used to run a light on the bicycle. So here, instead of using the power to run a light, we basically rectify the voltage and we charge a battery with it. And the amount of power you can get from it basically depends on the speed. So as your speed increases, you can harvest more and more power from the system. So now in a city, because you would keep stopping at lights and so on, your average speed is not going to be very high, and so we anticipate that we can only generate 1 to 2 watts basically while riding in the city. But on a more uninterrupted ride, like if you're going on a rural road, where you really don't have to stop and you can keep going, then you'd be able to generate 3 to 4 watts. Okay. Now that's not quite enough to power all the instrumentation on the bicycle. So we are estimating that we consume about 7 watts for all the sensors and the microprocessor and the speaker and all of those, all of the electronics on the bicycle. So what the Dynamo would do is it wouldn't really replace having to charge the battery, but it would extend the battery life by about 30% in the city and by over 100% for uninterrupted riding. So for example, if you were doing uninterrupted riding and you were using a 15.6 watt-hour battery, then instead of having to charge every other day, you could essentially charge once in 5 days. And so, it basically extends your battery life by quite a bit. It doesn't add too much of pedaling resistance, so the data basically shows that speed is reduced by about 2.5% if you use a dynamo. So it would add about 3 to 5 seconds per mile for an average bicyclist. So one of the anticipated uses of this dynamo is also to power basically a black box recorder, a video recorder. So so one of the things that Peter is also trying to do is have a video recorder that records 360 degrees around the bicycle, and that is entirely powered by the dynamo. One of the other somewhat surprising finds for us is that we can estimate the bicycle speed from the dynamo. So basically it turns out that the frequency of the alternating voltage that you get from the dynamo is the same as the frequency of rotation of the wheel, and so by having a frequency measurement chip you can measure the frequency in real time, and then you can estimate the speed of the bicycle. So we compared the speed that we get from the frequency measurement chip with the speed from a low-cost speedometer that we bought. Okay, so the low-cost speedometer basically has one magnet on the wheel, and so what it's able to do is every time you complete one cycle you get a reading. So it gives you a measurement of speed with a low resolution. It doesn't have a very high resolution. So you can see that the speedometer that we bought, updates only every once in a while. It moves in steps essentially, and you can also see that there is a time delay. So the dynamometer, the signal is always comes before the signal from the low-cost speedometer. So this is a good thing. We are able to measure the speed of the bicycle, and so that could potentially be used for all kinds of applications on the bicycle. Okay. So I'll talk about quickly about a couple of other things before I wrap up. One of them is dooring accidents. Okay, so dooring accidents. So that basically refers to somebody opening the door of a bicycle and hitting. Somebody opening the door of a car and hitting a bicycle. Okay, and there's not much data on how many dooring accidents actually happen. So we were able to find a little bit of data. So there's a report from the Illinois Department of Transportation that says that there were 302 bicyclists injured in 2015 in the state because of dooring. And then there is also a report that the Toronto Police Service reported 209 dooring accidents. Okay, so we don't really know how big a problem this is, but there was a focus group study that Nicole Morris and her group ran a few months ago, and so somehow that focus group felt that we should address dooring accidents, meaning they felt that basically this was a focus group of bicyclists, and so they were being asked, what do you think you need to be safe on the road? What kind of system would help you, and so on. So one of the things they mentioned is dooring accidents. They're just afraid of being hit by somebody opening the door on a car. So we looked into that a little bit. Basically it turns out that with the sensors that we already have on the bicycle, we might be able to do something. Now, on a car, you would be able to prevent a dooring accident. If you wanted to develop technology on the car, that would be a lot easier. So you could have, for example, a sonar sensor on a car, and if you find that there is any object, it doesn't have to be a bicycle, if there's any object within 1 meter of the car door, you could basically prevent the car door from being opened. So that would be pretty easy to do on a car. Okay, and if you wanted to provide, if you want to do more than that, you can use your blind spot monitoring camera to predict if a bicycle that is coming up from behind is going to be hit or is going to run into your door if you open the door, right? So you could do that as well. So these things are a lot more easier to do on the car, but we are not really working on cars. We are working on technology for the bicycle, and so so what can we do as far as helping prevent dooring accidents on bicycles? All we can really do is we can have a system that warns the bicyclist that he or she is riding too close to parked cars. So basically, if the bike is riding past cars that are parked on the road, you can basically tell that the bike is riding too close to cars, and you can provide a warning. Okay, you can't really know whether a door is going to be opened. Okay, that's really very, very difficult. From the bicycle, you can't really know when a car door is going to be opened. Okay. Now it turns out that the sensors we already have on the bicycle are adequate for this purpose. They could be adequate for this purpose. Okay. So we already use sonar sensors, for example, for detecting right-turning cars. We already have inertial sensors on the bicycle in order to find how much the bicycle is tilting. Okay. So using those sensors, we can find out if the bike is very close, if it's riding very close to a car. Okay, this is a system under development. So there's a sonar sensor here, and there is an inertial measurement unit. So this is a cheap inertial measurement unit from a company called InventSense, less than $10. It has a 3-axis accelerometer, 3-axis gyroscope, and 3-axis magnetometer. So we use all these sensors essentially, and what we are trying to do is, we use the sonar sensor to measure the distance and to see if there's any object very close to the bicycle. Yeah, and then we need to know if that object is a car or not. Okay, because you might be riding next to a wall, or you might be riding next to a pole or a garbage can or something, right? So you need to know if it is a car. And so what we're trying to do here is we're trying to use the magnetic field of the car. So every car has got a magnetic field around it. So we're trying to use the magnetic field of the car to detect that it is indeed a car, in addition to measuring the distance to it with the sonar sensor. So that is something that we've done some work on here. We can measure distance, and then we get magnetic fields from the magnetic sensor. Now the problem is that because of tilting and vibrations on the bicycle, you get a lot of changes in magnetic field. So there is, Earth has a magnetic field, and if your sensor was stationary, if I just had a magnetic sensor here, it would have constant readings. Because of Earth's magnetic field, it would have constant magnetic readings, and then if a car went over it, there would be a change in the magnetic reading, and you'd be able to detect that a car is going over the sensor. But if your sensor is moving all the time, and your bicycle is tilting, then the components of the Earth's magnetic field that your sensors are reading, those are going to change all the time. Okay, because you have a magnetic, so Earth has a magnetic field, and there's a magnetic vector oriented towards the North Pole, right, and that's fixed, and as your sensor moves, the components of that magnetic field are going to change all the time. And so you need, so what we found is essentially that, so this, for example, this data here, so in this data, this first reading here, that was from a car. So the bicycle was riding next to a car. This was actually because of tilting that the sonar sensor actually read the ground. So it actually was reading the ground, wasn't actually reading a car. And then if you look at the magnetic readings, there's not that much of a low frequency change in the Y magnetic field, but you can see that there is a change in the Z magnetic field, both when you're riding past the car and then even when you're not riding past a car. And you can see here that due to the tilting, the X magnetic field and the Z magnetic field both actually changed quite a bit. So we've done some work, and so these are preliminary results. This is something that we are working on. But basically what we do is we estimate the tilt angle of the car of the bicycle. We estimate the tilt angle of the bicycle because we have accelerometers, we have gyroscopes. Okay, so what the gyroscopes do is they measure angular rates. Okay, but you can't actually find angle by integrating the gyroscopes because you'll get a drift. Even a very small bias on the gyroscopes will give you a drift. You can never know the bias exactly. Okay, but then you have the accelerometers, and using the accelerometers you can find the static angle. So you can have a system that combines the static angle from the accelerometers and the magnetometer with the dynamic angles from the gyroscope, and you can estimate the angles. And if you do that, if you know what the tilt angles are, what we did in this case we modeled how the magnetic field changes as a function of the tilt angle, and then we removed that variation from the magnetic sensors, and then we are able to get a magnetic signal that is much more related directly to the presence of the car. So for example, here is some data here. So this is when the bike is riding past a car, and you can see that there is a change in the z-axis magnetic signal, which is the only magnetic signal that we are using, the z-axis magnetic signal. And then here, again, when you're riding past the car, there is a change in the corrected magnetic signal. On the other hand, when you're tilting, the change that happened in the magnetic signal due to the tilting, that has been removed, and the same here. So this is something that potentially could be useful. So this is something that we are still working on and trying to get to work more reliably. Okay, and then the last part of the talk. So there's also a human factors research effort in the project where Nicole Morris and her group are working on deciding what kinds of signals are most effective for alerting the motorist. So here the overall objective in the whole project is you're going to track all these cars, and then you're going to sound a horn or have a visual signal that goes on, and the objective is that the motorist should get alerted by these messages, right, and respond quickly. So if the motorist doesn't respond quickly, this is entirely depending on the driver really to respond. Otherwise, the system is not going to be effective, right? So what kind of signals would be most effective for alerting the driver quickly? So one of the things they did is they had a user group which tested 9 different sounds, and basically they got feedback from the users on which signals are more effective and which one they like better. So some of the attributes that they were looking at were things like bikeness, carness. So if you hear a sound, as a car driver, what do you think? Do you think it's coming from a bicycle, or do you think it's coming from a car? Are you more likely to look for a car around you if you hear the sound, or are you going to more look for a bike? And then it has to be something that conveys a sense of emergency, a sense of urgency, right? So they got some feedback from users about which of the sounds was more effective, and they picked one of the sounds as the sound to use, and that is this one here. So let me play that for you. Okay, so now I'll compare that with some of the others that they did not pick. Yeah, so so the user said the first sound was the best for this application. Okay, so that sound is like this. Okay, and then one of the future activities. So two of the things that they plan to do are a driving simulator study, and what the driving simulator study is there will be car drivers sitting in a driving simulator in a room, and then they'll encounter traffic in the simulator, which includes bicycles, and they might be provided warning or they might not be provided warning, and then they have to, and then how well do they respond to the presence of the bicycle and the occurrence or non-occurrence of warning. And then the other study that they are going to do is the influence on the bicyclist. So a mock study in a parking lot where what effect does the sound have on the bicyclist who's who's going to ride the bicycle and who's going to hear the signal. Okay. So one of the things they'll do in the car simulator study is look at whether the driver is able to localize the sound, whether the driver is able to see where the sound is coming from. So when the driver hears the sound, is he or she able to understand that the sound is coming from that direction, so the bicycle must be over there, or the sound is coming from this direction, so the bicycle must be here. So is it directional, and are they able to localize it? And we don't really know the answer to that, whether it's going to be directional or not. We don't know. We don't have the capability to use a directional speaker. Okay, so directional speakers are, they're available with the military. They're very, very expensive. Okay, so it's not suitable for us to use on a bicycle. Okay, so some other activities that we are also working on as a part of this project. There's various things like we are tracking all vehicles at a traffic. So we're trying to track all vehicles at a traffic intersection using a radar instead of a LiDAR or camera. So a radar is less expensive than a high density LiDAR, right? And so we are trying to see whether we can use a radar to track all of the vehicle maneuvers that go on at a traffic intersection, and we're trying to use a single vehicle model that works for all maneuvers and a nonlinear observer, and see whether we can actually track all the activity that goes on at a traffic intersection. So we are also looking at a black box recorder on the bicycle, as we said. And then one other thing that's going on is a smartphone app for notification of an upcoming traffic intersection. So basically, based on GPS and a map that tells you where the traffic intersections are located, we're trying to find out before we come up to the traffic intersection, we want to notify from the smartphone. So every rider is going to have his own smartphone, and so we have a signal that is going to go from the smartphone to the processor, the TNC processor on the bicycle, telling the TNC processor that there is a traffic intersection coming up, so that the TNC knows that there is a traffic intersection that is coming up. Okay. So that brings me towards the end of my talk. And so what are we doing in this project? We're developing a collision prevention system for a bicycle, and some of the modular components of that are a rear collision prevention system, right? So we talked about that. So that was based on the single laser sensor at the back on a rotating stepper motor. A right turn collision prevention. So this we didn't really talk about, but basically it's a sonar sensor, a custom sonar sensor that we have developed for seeing if there is a car right next to the bicycle that is going to turn right. And then the left turn collision we talked about. So this is based on the low density LiDAR sensor that is going to monitor all left turning cars at intersections. There's also human factors research going on to ensure that the alarm that we sound is effective and elicits a fast response from the driver. And so our future plans are to continue the technology development that we are doing here and do more extensive testing, and so get the technology more ready. And then subsequently, we are going to do a two-stage field operational test involving 10 bicycles. So at some stage, we'll start instrumenting a lot of bicycles. So we're going to instrument 10 bicycles. So we have an industrial collaborator called Quality Bicycle Products with headquarters in Bloomington, Minnesota. They are a big bicycle company. So they might actually even be the biggest bicycle company. I haven't really understood whether they are the biggest or not. But in terms of overall, I think in terms of sales of spare parts, they might be the biggest bicycle company in the world. And so their employees are going to ride our bicycles, 10 of our bicycles for 6 months. So we're going to get data from those bicycles, and we're going to see if the data shows that near collisions are prevented. Whether there is if there's data that can show that there really is an improvement in the safety of the bicycle. And so if the data shows that the system provides good benefits, then potentially QBP or some other company can commercialize that system. Okay? So that's all I have on the seminar, and I'm happy to answer questions. Yeah?
Do you have any concerns about the laser being so low to the ground where, like, I don't know, water and debris is going to be kicking up into this, and then is it still going to be able to track cars if it's, I don't know, getting dirty down there?
Yeah, that's a good question. I don't know the answer to that. So we have talked about, the fact that if the bicycle falls over, these systems are going to get damaged. So sooner or later, bicycle is going to fall. But we haven't really talked about water and debris. But there is certainly work to be done on making a nicely enclosed, robust system that is able to survive.
Any questions coming in? None? Yes?
Yeah.
I'm sure you already considered this, and you mentioned about the low density, the LiDAR system is more expensive for your side collision, for your right turning collision, right? But why not using the rear collision warning system, the single beam laser, for that type of application, and why you have to use the LiDAR system? So what is the constraint?
Yeah, that's a good question. The single beam laser sensor, we could try and do the same on the front as we are doing at the back, basically install it on a stepper motor and do scanning and tracking. It's definitely a more complex situation at a traffic intersection compared to tracking cars behind you. So tracking cars behind you, you only have to be concerned about one or at most two cars behind you. And so it's a lot easier to track those cars. Traffic intersection, there's a lot of stuff going on. You can have occlusion very easily, and so we felt that having a single beam is going to be inadequate. Ideally, we would, the ideal system would be the low density LiDAR mounted on a rotational platform, so that using that sensor, we are not only able to track the left turning cars, but also the cross traffic and essentially all the traffic at the intersection. That would be the ideal scenario. And so we felt that the LiDAR is a better bet to study for the traffic, for the traffic intersection case, because we have a lot more possibility of being able to track what goes on at the intersection. With the laser sensor, it's going to be pretty difficult, because you'll have cross traffic and and then opposing traffic. So all kinds of things. It'll be much more difficult to track all of those possibilities using that single beam laser sensor.
I have a ton of questions, but we're running out of time, so let's join me in thanking our speaker for a very interesting presentation.
Thank you, Max.
And next week, there will be a seminar, come again, same time, same place, Building a Freeway Laboratory for Connected Vehicle and Traffic Safety Research and Development. John Herdos will be presenting on that subject. Again, same time, same place, so look forward to seeing you there.
I think these systems have to be really protected in general. They have to be all protected, because I think
project